PhD at the UNISH. We'll give a talk about analytical exploration of nonlinear dynamics.
Yes. Thank you very much. So this is another switch of gear a little bit. I want to talk about nonlinear dynamics and how perturbative approaches can help us understand, in particular, how statistical features are processed by neural networks. And the that we actually have it working. Now we have it. Okay. The reason I want to look into perturbative approaches is that when we are looking at the brain, which is a very high-dimensional, time-dependent, and non-linear system, there's very little hope of really getting a functional understanding how statistical features that are once presented as inputs to this network are sent throughout and how are actually affecting the signals that we record. We know all of that, of course, and that's why we do modeling, right? But even if we go into the simplest type of model that we can imagine with these properties, for example, a recurrent neural network, which is high dimensional, it has a set of units, a set of neurons, basically, that represented, it has some time-dependent dynamics, and a nonlinear activation function that governs the next time step. Even such a much more simplified system that doesn't have any of the biological details is in some sense still a black box to us. Which means that there's a lot of things we can do with lots of models, of course. But for example, if we want to understand how a little change in the parameters really affects how the signals are transmitted and how it affects how the network state evolves in time later, basically the only thing we can do is brute force evolving the system, or we can do some sort of back propagations. But that's not what I mean when I want to really understand what's happening in a model. For this reason, I'm going to simplify this already much simplified model even a little bit further, just as much as we need. And instead of making it just arbitrarily nonlinear, I'm going to look at recurrent neural networks that are operating close to the linear regime. They are still nonlinear, but only weakly so. Because that is something that allows us to look with perturbative methods into how statistical features that are present in some input time series we present to it really affect the outputs. And today with this system, I want to ask 3 questions. The first one is, okay, let's start with this close to linear recurrent neural networks. How can we understand the dynamics in that case? It's still a nonlinear recurrent neural network. The second one is, once we understood that, how does that affect how statistical features are processed? What does that mean for the transmission of information by such a system? And then the last question is going a little bit in the direction of well, we can't just look where we have light for the key that we lost, right? What do we do if we don't have a system that we can just perturbatively analyze and decompose analytically? How can we still study how statistical information is transmitted? So I start with the first question, which is, let's start understanding in a weakly nonlinear recurrent neural network how the dynamics is dependent on the signals and on the parameters that we have in the network. But before taking the step of weakly nonlinear, of course, we have to look at the baseline that we can actually really solve and understand, which is the linear system. So we have a linear recurrent neural network. We have it here. So we have our neurons Y. They are recurrently connected all-to-all or whatever you have with some connectivity matrix W. Could be sparse, could be anything. We have some external input that is fed into the network. And we want to know how do the network states Y evolve in time? And in a linear recurrent neural network, you can express this with an equation of motion, of course linear. So it has 2 types of input, the external one here and the recurrent connections. And because this is just a linear differential equation, it is fairly easy to solve, which means that the network state at some given time t will just be an integral over a fixed function that depends only on the network parameters, like the connectivity matrix W. This is just like, what's it called? Cutoff for the time parameters and everything. So it's a very simple matrix exponential, basically, that is integrated over with the external stimulus. Okay, what this means is what we can represent this equation that we have here, this whole recurrent network now, instead with one linear mapping. So this more complicated recurrent network, I can just represent it with this single line, where this line I represent this matrix exponential integration with. Okay, so that is a linear recurrent neural network. Linear functions only to do so much though. So let's now look into the case where we start perturbing and look into a nonlinear recurrent neural network operating close to this point though. Okay, so generally in a nonlinear recurrent neural network, I would have some arbitrary activation function. I put it here around the network states. And when I'm saying I want to have it in a weakly nonlinear state, what I'm basically saying is I want to be able to make a Taylor approximation of this gain function. And I say I keep the lowest order here, so I'm putting here a small quadratic nonlinearity. Sorry. And now when I have an equation of motion that is very similar to the one that I could solve before, I can also hope that the solution to this equation of motion will be very similar to what I had before. So I will make an ansatz for solving this one, which is called a perturbation ansatz. So I say, okay, let's try and not solve this exactly, but approximately, and give different contributions to my network state evolution. I say, okay, if this term wasn't there, if alpha was 0, then I should come back to my original solution to the linear system that I could solve exactly. And then for any alpha, no matter how small it is, I should still be able to solve this contribution by contribution. So what this means, I can plug in this network state evolution into my equation of motion and then solve it order by order for alpha, because for each alpha it must be like solvable independently. Okay, very good. If I leave out all terms that have an alpha or more than one alpha, I come back and get the linear recurrent neural network. That's great. That's exactly what I wanted. That means that the baseline of my solution, the main contribution here, because alpha is small and there are only higher contributions of alpha, the baseline will again be the linear dynamics. That's exactly what I wanted. Now let's have a look at what all of the terms look like that have at least have exactly one alpha in there. And what happens to come out is that the equation of motion looks nearly exactly the same, with the only change that this external stimulus is now replaced with a term that depends on the linear solution by 0. And it depends on it quadratically. But if you know a little bit about differential equations, that means that gaining, like solving this function, is pretty straightforward, because you can just replace like this external stimulus term, you can just replace it with the lower order term that we've already had. And that means that we can actually like directly write down how this additional contribution, y1, looks like. It will just be the integral over this linear Green's function with now this recurrent input. And I'm now introducing this diagrammatic version of writing this, because what you can see is that, well, this y here is like propagated linearly from some input. And here the input was x of s. But now this input is something that is like connectivity and already some linear movement squared. So we have here like this branching of the diagram into two parts that are already the linear movement. And in fact, for all of the higher order contributions, I can continue doing this, and I will get tree diagrams that have more and more of these branches, but also have more and more of these alphas, and because we choose alpha to be small, become less and less relevant. Just 1 second. So the consequence where we're going to go to is like, what does this do with the transmission of information, with statistical information in particular? And if I now look, I will just replace all of this function here with just another shortcut called G2. But I only look at like how the input is actually mapped to the output now. What you can see now that in addition to this linear mapping where one instance of the input X is mapped to the network state Y, I now have an additional contribution where the quadratic, like X is mapped quadratically to the output. And I would get more and more polynomial factors if I included more and more orders here. So this is first of all like giving us an idea of like how the dynamics of the recurrent network looks like. What about like the propagation of statistical features now? I want to tell you that on one example, and that example is called reservoir computing. We've heard about that already a bit yesterday. In reservoir computing, we are taking a recurrent neural network with some random arbitrarily chosen weights. And we want to use it to classify time series. So we have here time series that belong to class A and B that have some shared underlying characteristics. And because these recurrent networks, we also heard about that yesterday, basically are like sets of feature detectors that compose into different modes with different time scales, different frequencies. Basically, there are happening lots of different filters on top of these inputs that I give them. And if there are some shared characteristics in them, it's very likely that even for a random network, that the time dynamics here will be separable after a certain amount of time. And in reservoir computing, therefore, one just takes that and trains a linear readout in the end on the network dynamics and says, okay, I want to separate the classes as much as possible. I maximize the margin, which means like the smallest of all of the distances of these points to this hyperplane, and I maximize that, bring them as far away as possible. And that's just called reservoir computing. Okay, but we now have an idea of how, with a certain network, how the inputs are actually mapped to these network states. So that means we can ask the question how the statistical features present in this input actually affect also the statistical distribution in this output, in this readout. And in fact, we could like use a bit like the filtering properties of this recurrent network that just has lots of different mappings, and ask like, maybe I can also optimize, for example, this input projection so that these statistical features are just taken up as good as possible to increase the separability of these clouds. Okay, so that's what we're going to do now. In order to do that, we have to first express, of course, like the separability that I'm talking about, and then maximize it, right? So I said already before, the typical objective here would be the margin. So with network states Y and a hyperplane whose normal vector is V, I can get the distance of any of these points by that scalar product. Theta is just a label plus minus 1 because we have different sides here. And then the margin would be the smallest of all of these distances, which we want to maximize. Usually that is a fairly simple problem that's solved with support vector machines. However, they can only do that because this is a linear relationship. And we have learned now that our network state Y depends quadratically on the input. So we would have to like do back propagation or something like that, a gradient descent or something like that, on a minimum function, which is not so well because it's like not everywhere differentiable and stuff like that. So I'm doing a little trick here. You can recognize again here the argument of this minimum, which was the distances of the points to the hyperplane. They are scaled by a control parameter eta. And then we have a sum of exponentials. And if eta is large enough, or the distances are like varied enough, then the sum of exponentials will be dominated by the exponential belonging to the smallest distance. And then I'm inverting all of this again. What this means that if I choose eta large enough, in praxis, it doesn't have to be that large, honestly, this margin, this function that I call the soft margin, actually approximates the margin very well. Okay, I'm also avoiding this minimum function. It is everywhere differentiable. And one further point, instead of like typical support vector machines, which just care about a few points that are very close to the hyperplane, it is now dependent on all of the states. And it's interesting that it depends on all of the states, because what I actually care about is the statistical feature. So I can look at the statistical distribution. And here's one of the clues. This type of function is something we can know from physics very well, which is called a cumulant generating function. The derivatives of this function here are the cumulants of the statistical variable that we have in here. More about cumulants I'm going to say later, but if I do a Taylor approximation of this soft margin, I'm stopping now after the second contribution. I'm getting contributions that have very good geometrical interpretation to show us, to guide us about like why I call this a separability. So for example, this first term here is the mapping of this mean separation between the classes on the readout direction. Second contribution, on the other hand, is the mapping of like this variability of the classes in themselves, also again in readout direction. So if I'm maximizing the soft margin, what I'm really doing is I'm driving these clouds away from each other by keeping the fluctuations in readout direction low. Okay, so let's have a look into how now the network dynamics actually influences these like first to cumulate the mean and the covariance of the network states. We have seen that when we have this linearly recurrent neural network, that we can decompose it into a series of mappings where polynomial and increasingly polynomial combinations of the input are mapped to just the network state. So if I compute now, for example, the mean separation between the classes, which is just averaging over the network states y, I'm not only averaging over x, I'm averaging over x squared. And if I take higher orders, I'm averaging also over higher orders of that, which means I'm getting information from the covariance information of the input into the mean separation between the classes. Okay, from the covariance is moved into the mean. I'm getting higher order information into the lower orders. And the same is true also for the covariance. There I'm even getting up to fourth order information just from the first order small correction here that I have from this weak nonlinear gain function. Now, the thing is, generally, these contributions are not independent, but they are also not like necessarily aligned with one another. Which means that if we optimize now, we have these contributions, the main one from the linear network and a little bit from that small nonlinearity, they could point in general at anywhere. So if we now look what optimizing actually this input projection does compared to just classical reservoir computing with a weak nonlinear reservoir, then it is very little surprising that for random input projections, this weak nonlinearity, I have here like a value of 0.0, is not doing very much. So the separability, the soft margin of nonlinear system is very, very close to that of the linear system. But as soon as I optimize, not only I'm getting quite significantly like better separability than I had with random input projections, but there's also a gap here that the nonlinear separability is getting better than the linear one. And this effect becomes more and more important the more difficult the task is. Okay. I don't want to go too much into the results in this. I just want to show you before I continue that you can also do some actual process some actual data here and not just some benchmarking. So this is classifying heartbeats into health disease subjects, and I just want to have you see that here on the right-hand side, you have a much better stability of the classes compared to random input projections here, just to see that you can treat actual data with this. Okay, so we have seen that higher order statistical information in the input is moved to lower order statistical information in the output now. But what do I do now if I do not want to use a weakly nonlinear recurrent neural network? That's a very specific type of model. And I would argue that we should still test for how different statistical features are processed by whatever model we're doing. But in order to test that, well, if we can't analytically unfold them, we have to do that numerically. That means we need to have like benchmark data. We have to have a data set that actually has the features that we want to test for, and then see how the different statistical features, for example, compete with one another. Which ones survive? What is the network sensitive to? Is it maybe like not even sensitive to covariance information when I'm actually caring a lot about covariances or something like that? And this is a problem that, first of all, we have to look a little bit into like how can we generate data that has statistical features that are exactly the ones we want, right? Now it would be so easy if it was only mean and covariance we cared about. Mean and covariance are cumulants, the first two actually, which define a probability distribution. But a probability distribution is defined by more than only mean and covariance. For a Gaussian, that is all you need. A Gaussian only has these two features. It gives you like the center, it gives you the width, and the shape is completely determined by that. But actually, any probability distribution that you have, you can express very much in a sense of like a Taylor series, where all of the different orders are the so-called cumulants of the distribution. And in fact, the Gaussian distribution is the only one that is that simple, that only has a mean and covariance and nothing else. And all other distributions would have some higher order information in there. For example, what higher order information could be, sorry, please excuse this very ugly sketch, but if you had a distribution that is skewed like this, then you would have, for example, a very significant third order cumulant, which is like non-zero in this case. Okay, so now we have an idea of like what the statistical features are roughly that we want to create, but we're still having one problem. Creating data with certain cumulants is a bit of the inverse of a problem that we usually have. If I have a probability density, I can compute the cumulants. I can compute the mean by just integrating x with probability density. And the covariance, I have to do something like x squared and other terms. And I can do the same for all of the other cumulants. But here I want to go the other way around. I want to say, I want to have these cumulants. I don't care what the distribution really looks like. I just want to like have these Taylor coefficients to tune about. So how do we get all the way back? And I would say one way we can do this is, again, doing some perturbation approach. And the baseline for this perturbation, in this case, is not the linear model, but it's equivalently the simple model, which is the Gaussian. So in the Gaussian distribution, I'm like expressing it here in form of a Boltzmann distribution just because it has some nice statistical properties and I can use it later a bit. In the Gaussian distribution, we all know I'm leaving out any shift here. So we have zero mean, we have a covariance, which is just the inverse of this matrix, basically, and all higher order information is vanishing. Okay, and I'm not going to go into any details about how this is done now, but if I want to create higher orders, I will do very much the same that I did with the recurrent neural network. I will introduce a perturbation term, which is now a third order polynomial. So I have a tensor here with 3 indices, and basically I'm using x cubed just to disturb this quadratic potential. And now what I can do is I can take my baseline model, my sortable baseline model, and what I had before as this linear mapping that with the little arrow as the first order Green's function, I can now assign to this covariance. I'm just expressing it with a little line here. And what I did before was like this quadratic interaction becoming like this little node in my diagram will now be governed from this term. And in fact, if I want to compute, like for example, the mean here, I can create diagrams out of these little building blocks. And for the mean, I will create diagrams that have one external leg. And then I can like transform that back into an equation and say, okay, I happen to know that around this dip, around this center that's given by the Gaussian, this is disturbed a little bit by this cubic potential. My mean will be shifted a little, and it will be given by the parameters dependent on how strong this actually is. And I can do the same, and I can compute also the third order cumulant, which will have 3 external legs now. And then I can just plug that in and compute that. And why does that help me? Well, I said I want to have certain cumulants. If I have the covariance, that means I now know this matrix J. If I know J and I know the third cumulant that I want, that means I know K. And if I know all of that and I want a certain mean, well, I can just shift the data. Okay, so this is telling us that basically we can create and tune the cumulants that we want just by modifying a little bit the parameters in this model, and then drawing sampling from this Boltzmann distribution in whatever way we want. Of course, and very attentive people maybe have already clenched their fists under the table. Having a cubic potential in a probability distribution doesn't make any sense. You could never like integrate over the whole space, right? One of the edges would go to infinity, and then you can normalize that. That's why we are only in a perturbation approach, and it's so important. We are only like close to the minimum that would be given like by the quadratic function that's here, and we have to make sure that the samples that we sample are not going too far off. So, for example, so you can use whatever is your favorite sampling algorithm to get data that now has the cumulants you want. Just have to make sure that you don't go too far astray. It's all just an approximation. And one thing you could do, for example, that I like is there's this differential equation that we know that that has the Boltzmann distribution as a limiting case, and then we introduce a potential barrier and say, okay, I just don't allow any samples to go down there into the abyss, and that's fine. Okay. So one last thing is that I want to show you that we can actually like use data that's created like that. So in this case, I'm using this benchmark data to test a perceptron model that has been designed to have a trainable gain function. And this trainable gain function is putting in competition for the different statistical orders. So this order, the alpha 1, would be sensitive to only the mean. Any other higher order information, if we only had like a linear gain function, would be completely lost because later we're doing the average, and the output would not be affected by any higher order information in the data. And likewise, we have terms that are just dependent on the covariance on the third order polynomial here. I don't want to tell you about this model or why we're doing this too much, other than that we're trying to see the competition between these different factors. But I want to show you that we could create data. So each and every single one of these pixels here is a data set that we trained on. And the color code is telling us what the network thinks, like what is the best kind of combination of these gain functions to use for classification, to filter to the and have information on the data. So for example, here in the very right, on the x-axis, we're increasing the difference between the covariances of two classes that we wanna classify. And on the y-axis, we're increasing the difference between the third order cumulants of the two classes. And then the network has to basically decide like which of them to throw out. It can basically classify on both of them very well. Yeah, but in this way, that's the point. You can create all of these data sets for all of these pixels and just check your model, like how does it actually react to certain statistical features? What is getting lost when we send that in? Okay, and with this, I would like to wrap up shortly. So I wish I could like show you how we can use the so-called Green's functions with this perturbative approach to make at least a weakly nonlinear recurrent neural network accessible to us in terms of like analytically understanding the dynamics. That I could show you that higher order information from the input is mapped to lower orders in the output by nonlinearities in general, but in particular also even by weak nonlinearities. And then that when we cannot access like our dynamics analytically, at least we can create data that has certain statistical features that we can use in whatever way we want. Okay, thank you.
Any questions?
Much more.
I would like to ask.
Yes.
When you showed your last results, how do you go from your sampling the distribution to your time signal? Like.
In this case, actually, because this is a very specific type of perceptron, so a perceptron per se, like if you want to use a feed-forward model like a perceptron to classify time series, that's not usually what you would want to do, right? Because there's not a natural way to process actual time forward movement. In this case, we use it, therefore, like in a more hand-wavy way of like seeing like we're having a snippet. What I'm trying to say here is that each and every time point is sent through this nonlinearity independently. And in the end, we have a time average, which is like representing that maybe in the brain, for example, like the local history maybe is like on average influencing what's happening next. The point is that if we create a perceptron like this and we average over this time window, it does not matter in what order like the time points are. So for this model, we do not care whether there are any correlations also across time. We only care across channels. If we wanted to create data that also has like a certain correlation across time, well, that's fairly easy. You just have to create data that like uses the time points in case of what I did here with the channels and like the different inputs here, and you can do that.
Thank you for the presentation. I really like the part that you mentioned that by jointly optimizing not only the output weights as you do in vanilla reservoir computing, but also the input can improve performance with increasing task difficulty. So I was wondering if you have any speculation or any indications from existing data that this happens in real brains, or like a model system that could implement something like that. Yeah.
I think I'm probably one of the least qualified in this room to say what's happening in the real brain, honestly. As you may have guessed from like the type of my talk. So I'm not an expert on like real brain recordings. I have to say that. What I like to think about in this case is that when we're having like this recurrent network, and I'm optimizing the input projection and the readout, I see it that we cannot, every time we learn a new task, of course there's plasticity and everything, but we cannot completely restructure the whole network every time something new happens, right? And I think the reuse of existing structures by, for example, just changing how things are mapped into, by just having, for example, a Q-filtered way of saying, okay, I'm now sending information like this in, and now I have a different context and it's sent in a different way. That might be a way to explain, like, at least that's my way of thinking it, how a fixed neural network can handle the same input in very different ways, which are for different things. So that's how I'm thinking about it, at least. But in how far the actual brain does that, unfortunately, I cannot tell.
Do you make some assumptions on the structure of W? I'm wondering, like, if you have some correlated connectivity or some structure in the connectivity, then your intrinsic fluctuations may already be so big that this analysis might not work.
That is a very good point. Let me go here. Okay. Wait, that's not the good way. Here. Let's talk about the linear system first. In principle, for solving this linear differential equation, W can be anything, of course. However, if W has eigenvalues that are larger than 1, then this exponential function, of course, just blows up. That means that, that's the point of linear instability. We heard about that yesterday also, but that's the point where the dynamics we gain become unstable. And if we now would go into the nonlinear system, where we see this is then put in quadratically, at that point, everything just doesn't make any sense anymore. Other than that, you can put in sparsity or everything, right? So the question is it is still only a recurrent network model with recurrent units. There's not much biological realism in this very simplified view. So I would not say and take a recurrent neural network, and if somebody gave me the weights measured in some neurons and say, okay, I just have to replace those weights with that weights and be done. That's not how this works. So this is an effective model basically in that sense also.
So that's fine. I was only thinking if you assume that there is some shared connectivity or things like that, meaning network itself introduces more correlations than there are in the inputs.
No, I don't make any further assumption on W.